Hey guys, Mr. Ye back again, and today I'm going to be covering section 2.1 from our textbook, which deals with linear relations and functions. So as the first section in a new chapter, a lot of the times there are just a lot of concepts being covered, some vocabulary to make sure everyone's on the same page, some things that you've probably seen before, but kind of refreshing them, maybe going a tiny bit deeper. And that's kind of what this section is. So we're going to jump around a little bit to a few different topics today. And just get us that firm foundation for moving forward in chapter 2. So chapter 2, 2.1, section 1, deals with linear relations and functions. And the first thing I like to highlight here is just that word, the root word of the word linear, and that is line. We are going to be talking a lot in this chapter about lines. Lines are inherently straight, they go on forever, and so a lot of the functions we look at are going to have to deal with lines. So before we jump into lines, we have to define a few terms first, and one of those terms is set. What is a set in mathematics? There's actually an entire branch of mathematics called set theory, which is really interesting. We don't get to cover it too much in this course, but for our purposes, what is a set? Well, a set is a collection of distinct objects, no duplicates. So every item in the set is only appears in there once. It might represent duplicates, but it only appears in the set once. And I'll demonstrate that here in just a second. Sets are usually sorted into some logical order, not always. The reason we try to sort them is then it becomes easier for our brains to kind of see what's in the set if we go from lowest to highest, for example, as opposed to just a bunch of elements in there in no order. That's harder for our brains to kind of search for something or process what it is. And then finally, sets are denoted with these curly braces that I just highlighted. If you see those curly braces, you know you're dealing with a set. So for example, if we have a bunch of student ages here, these look like students who are maybe in a high school, those are their ages, and I wanted to write a set, I could do so like this. I could say, well, S may be for students. I can call it whatever I want. Sets are usually denoted with capital letters. S equals, and then I'm going to try to put the elements that should be in the set, try to put them in ascending order, least to greatest. So I look through and I say, okay, 14 should be in this set. And that actually takes care of all the 14s. I don't have to write 14 again, because remember, sets always have no duplicates. They are distinct values. So 14 there. 15 comes next, it looks like, and it takes care of a lot of the elements in my original list. 16, we have 117, and then 118. And that is the set of student ages as it's given to us. There's another way, there are actually a few different ways to write sets, and so I'm going to try to show you a variety of them. Some of them will be more useful now, some of them will be more useful later, but this next one I want to at least introduce now, so that when we get to later, when it is really useful, you've seen it at least once before. You'll notice that our set is just the whole numbers, the integers from 14 to 18. And so when there's a pattern like that, sometimes it's easier to list it out using something called set builder notation. So I'm going to come off to the side here, and I'm going to write another way to write this set. I'm still going to call it S. So S equals, and then I'm going to draw my curly brace to say it's a set. Now here's where things get a little different. I'm going to write a couple things down, and then I'm going to explain what all of them mean. All right, this is the set builder notation for representing that exact same set that we just saw. So how does this work? What does this look like? Well, this is saying that the set S is all of the x's, and x is just a variable that we're using. We could have named it any letter, but we're using x. All of the x's, that vertical bar is pronounced such that, meaning we are listing out in this set all of the x's that meet certain criteria, all of the x's such that x is an element of, that's what that funny looking E means, is an element of. And so we're looking for x's that are elements of, now what's up with this n, this kind of double-stemmed m? This double-stemmed m is the shorthand way of writing natural numbers. And if you don't remember, if you haven't seen what natural numbers are all of our positive integers, 1, 2, 3, 4, 5, 6, and it goes on and on and on. And so that double-stemmed n means all the natural numbers. So let's read what we have so far. S is the set of x's such that x is an element of the natural numbers, so it has to be an element of the natural numbers, one of those positive integers, comma, 14 is less than or equal to x is less than or equal to 18, meaning x is a natural number and it's in between 14 and 18 inclusive, including both of those boundaries. So this is called set builder notation, and what we wrote kind of towards the right-hand side there literally builds the set for us. It says, take all the natural numbers, then only keep the ones in between 14 and 18, inclusive. You might say that seemed like a lot of work. It was easier to just list them out. And on this example, I would agree. But think about, what if we had to list out the numbers 14 through 201? Well, then that would take a lot of time and paper to list out every single number. Whereas with this set builder notation, what's the only thing that changes? Change that 18 to a 201, and we've listed them all out. The set builds itself for us. Natural numbers between 14 and 201. So we will see set builder notation a little bit more. Like I said, not super important and useful today, but hopefully that at least gives you an idea so that next time you see it, you'll have a starting place. Okay, let's do one more set example. We won't do set builder notation on this one, but we're looking at sophomore test grades on some exam for school. So maybe I call this T for test grades. And I'm just gonna list them out again, lowest to largest. So looks like 54. Then I see some 70s, so 76, 79. Not gonna list 79 twice, don't want duplicates. 85, 90, takes care of both of those. We see 92, 93, and then one sophomore earned a perfect score, assuming this is out of 100. So we can just write a set like that. And I mentioned we're not doing the set builder notation with this example. Biggest reason is there's not really a nice pattern, right? We didn't say everything from 54 to 100 because there are a lot of grades in between that weren't necessarily earned. So in this case, it makes sense to just list out all those numbers. So now that we've talked about what sets are, let's see why we needed to know what a set is. Well, because this next definition that's coming on the screen right now involves the word set in it. A relation, what is a relation? A relation is a set of ordered pairs. And if you don't remember what ordered pairs are, look at that first kind of clarifying bullet point. An ordered pair is just a pair of values, oftentimes coordinates, like for a point on a graph. So x comma y, for example, that is an ordered pair. So a relation is just a set of ordered pairs. And you can see down here, this relation that we're given on this sample problem, there are the curly braces showing it as a set. And what is inside the set? A bunch of ordered pairs in those parentheses, okay? So before we dive in though, let's talk about these other two. Domain, and I'm gonna draw an X there, I'll explain why in a second, and range, I'm going to draw a Y there. Domain and range are always talked about in the same sentence. The domain of a relation, as you can see from what's on the screen, is the set of first coordinates of the relation. So if we have ordered pairs, if we have x comma y's, then the domain is the set of all x's that we see in this relation. And so down below, when I'm asked for the domain, I'm going to pick out all those x values. So I see 2, I see 3, I see 10, I see -2, I see -3. I'm going to put them in ascending order. So I'm going to start with that -3, -2, +2, +3, and 10. That is my domain for this relation, all of the x values that we see. Range. Range, if you look at that definition, the set of all of the second coordinates, in our case, the y coordinates. X comma y is typically what we use, not always, but most often. So for this range, I'm going to say r equals, and pick out all of my second coordinates, my y coordinates, 3, 8, 99, 3, and 8. And I don't want duplicates, remember, only distinct values. So I'm just going to say 3, 8, and 99. And that set represents all of those second coordinates that we had in our ordered pairs. Okay, domain and range are going to be popping up the entire year long, as well as next year, as well as the year after. We're really never going to get away from it. So it's a great thing to learn now. And if you need to rewind at this point and listen kind of to that explanation again, feel free to do so. That's one of the good things about these videos. So there are a couple different kinds of relations that we're going to look at. And so I'm putting them on the screen right now. The first type is what's known as a discrete relation. And so a discrete relation is a relation where all of the points are not connected. They are just individual points out there floating around. As you can see from the graph, it almost looks like a check mark. Those points aren't connected. We don't draw a line in between them. And over here on the right-hand side of the screen, you'll also notice the relation itself. There's the set. There are all the ordered pairs, 2, 2, 1, 1, 0, 0, -1, -0.5, -1.5, 0. So discrete relations have discrete points, points that are not necessarily connected. Contrast that to the second one on the screen, a continuous relation. And a continuous relation is a relation that has an infinite number of elements, and they are connected. Connected with a straight line or a parabola, or there are many, many, many shapes it can take. But what do you notice about a continuous relation? Well, it has sort of an equation. It has a formula. And we can plug any x in and get any other y. And that's why it has an infinite number of points, because there's really no limit to what we can plug in there. So a continuous relation, does it have individual points? Yes. Here's one individual point, and here's another one, and here's another one. But there are an infinite number in between those points I just drew, and all these points are connected. So that's what makes a continuous relation, if they're connected. So we're also going to be talking about functions today, both graphically and algebraically. And so to start, I just want to go with one of the most important concepts that you can get right now, which is this whole f of x idea. F of x often confuses people at first. They say, is that f times x because there are parentheses? The answer is no. Functions usually, most commonly denoted with f of x, are basically something where we plug in a number or a value, an expression, we plug something in and we get something out. And the input is whatever goes inside those parentheses, f of x. And then we use that input to calculate whatever the function rule tells us to, and we get an output. And so over here on the side, I want to demonstrate that really quickly. So on top, we have f of x equals 2x squared. What that means, that general function rule is telling us whatever we plug into these parentheses, we're also going to use it to replace this x. We're going to square it and then multiply it by 2. So f of 3 is going to be 2 times 3 squared. 2 times 3 squared, we're plugging that 3 anywhere we see an x in that general function definition. So 2 times 3 squared, we know our order of operations. We should do the exponent first. So 2 times 9, because that's 3 squared, and we get 18. So f of 3 is 18 in this problem. What about f of 5? How do things change? Well, the good news is not much. F of 5 is going to be 2 times, now we're not plugging 3 in, we're plugging 5 in. So 2 times 5 squared, which equals 2 times 25, which equals 50. F of 5 in this example is 50. Which brings us to the third example, the third and final one for this function. What is f of smiley face? And this sounds ridiculous, this sounds nonsensical, and in some ways it is. But I like including this example just to drive home the point, look, we know how to deal with functions. Whatever is inside those parentheses, that's what we're plugging in for x in our general function definition. So what is f of smiley face? Well, it's 2 times smiley face squared. And we don't have mathematical rules for how to square a smiley face, so I'm just going to leave it there. But f of smiley face is just 2 times smiley face squared. We can plug in smiley face. It doesn't make much sense mathematically, but that's how functions work. Whatever is inside those parentheses, we plug in for x. What about this second set right now? I want you to pause this video, and I'm going to pause mine and I'm going to work them out. When you're ready with f of t, and then those 3 problems, f of 4k, f of 10, and f of star, hit play on the video and come back and make sure that your results match mine. I'll kind of talk through it, and then we'll go from there. So pausing the recording right now. All right, we are back, and hopefully you paused it and had a chance to work out those examples. We're given a function f of t equals 7t minus 3. And so as you can see from my work, I just took those various inputs on our 3 problems, 4k on the first one, 10 on the second one, and star on the third one, and plugged them in for x. So on the top one, 7 times 4k gives me 28k minus 3, and there are no like terms I can combine at that point. So that's my final answer. The second one, f of 10, I plugged in 10, I got 7 times 10, which is 70, minus 3, so 67. And then finally, kind of like f of smiley face above, f of star, I'm just going to plug in star anywhere I see an x, so 7 star minus 3. I don't know my mathematical rules for how do I do 7 times star. Maybe it's 7 stars all in a row, but I'm just going to leave it 7 star minus 3. Remember, whatever is inside those parentheses, that's what we're plugging into the function. So hopefully that made sense. Hopefully you had some success on those exercises, matched mine. If not, pause it, rework them, make sure that you see kind of the difference between our work, rewind if you need to, and only go on when you're ready. So functions, that was kind of algebraically how we handle functions, but how do they relate in 2.1 to everything else we've been talking about? Well, a function is a really special type of relation. So you can see from the diagram below, all functions are relations. If it's a function, it's automatically a relation. But not all relations are functions, and here's the special rule. A function is a relation in which each element in the domain is paired with exactly one element in the range. That means that each x only goes to one y. I'll say that again. Each x only goes to one y. That's what makes something a function. So a single x value does not have 2 different y values. And so graphically, this is what this means. On the left, red, not a function. Because whatever this x value is, I'll call it 7, why not? Whatever x value is right there, it not only goes to this positive point on the graph, it also is going to this negative point on the graph. What are the ordered pairs? 7 comma positive something right here, and 7 comma negative something right here. So that x value went with two different y values. That means this is not a function. The second one, the green example on the right, that is a function because every x only goes with one y. I could search and search and search and say, what about this x? Well, it only goes with this one y on the graph. What about this x? Only goes with this one y. Some of those lines are kind of steep. It looks like it might go with more, but for example, like this x goes right here and it never hits it again. So as you see at the bottom, and hopefully you've heard this before, we can perform something called the vertical line test to see if something is a function or not. The vertical line test says if you can draw a vertical line anywhere on the graph and it hits the graph more than once, then that means it is not a function. So that's what's shown with this red dotted line here. We hit twice. We hit twice in that same vertical line, not a function. Whereas on green, nope, I only hit it once there. I only hit it once here. Don't judge my vertical lines. I only hit it once here. I only hit it once here. So I couldn't find anywhere on that green graph where I hit it more than once. That means it is a function. So the vertical line test used to tell if something's a function or not, making sure each x only goes to one y. All right, so if it's true that each x can only go with one y, then are those two discrete relations on the screen right now, are they actually discrete functions? Let's take a look. Let's take a look at the first one. We've got 2 going to 5, so 2 comma 5. We've got 3 going to 5. Is that a problem? No. We can have multiple y's on our graph, but each x can only go with one y. 6 comma 2 is not a problem. This looks like a problem though. We had 3 as an x value going to 5, but then we also had 3 as an x value going to 10. This is not a function because that one x value went to 2 different y's. How can we fix it? I mean, this is kind of just a side note on the right-hand side of the screen because we can't just change functions in most problems, change relations, I should say. But right now we are going to. How could we make this a function? Well, if this 310 had not been 310, if it had been 410, would that work? 2 goes to 5, 3 goes to 5, 6 goes to 2, 4 goes to 10, and there's no single x value that goes to multiple y values. So that would work. 5 comma 10 would work. Basically just anything that gets rid of the duplicate x value would work to make it into a function. What about the second relation on the screen? We see 2 going to 5, we see 3 going to 5, we see 2 going to 6, and immediately that's a problem. 2 going to 5, but 2 also going to 6. That single x value going to multiple y values, that means it's not a function. So let's change this. Let's change this to, instead of 2, 6, let's make it 1006. Why not? If it's 1006, then we don't have any duplicate x's going to different y's. And so again, in most relations, we can't just change it to make it a function, but I just wanted to get your mind thinking about what would make it true so that although this was not a function to start, what simple change could we make to make it a function? So last thing for today, I've got 6 graphs on the screen, and I want you in a second to pause this video and think to yourself and reason out each of these graphs. Are they relations or functions? And are they continuous or discrete? Using some of that vocab that we've talked about today. So I'm gonna pause this video and then I'll come back and talk through them. But think to yourself with each of these 6, is it a relation or does it meet those qualifications for a function, that vertical line test? And is it discrete or continuous? So pause the video, take a few moments, and then go ahead, hit play. All right, so now that you've had a chance to look at these 6 graphs, You can see I've added my determinations as to what they are, and I'm going to talk through them really quickly. This first one, top left, this looks like a continuous function. It's not just a bunch of disconnected dots. It is a smooth line or curve. And nowhere on here can I draw a vertical line and hit this graph more than once. I'm always only going to hit it once. This is a continuous function. As is the second one right next to it, continuous function, again, smooth line, smooth curve, I should say. And so we know it's continuous, and no vertical line hits more than once. And so that makes it also a function. The third one's a little trickier. The third one has the potential to really trip us up. It is a continuous function. It's a smooth line, a smooth curve, I should say. I'm used to saying line because we're in chapter 2 with linear stuff mostly. But this is a continuous function. Nowhere can I draw a vertical line and hit more than once. The thing that usually throws people off is they say, wait, it stops though. It doesn't go on forever. So how is it continuous? Well, it's continuous where it is defined. It is all connected where it's defined. Yes, it stops. Yes, it stops or starts, however you want to look at it, but it is a continuous, because they're all connected where it's defined, function because it passed that vertical line test. The fourth one, getting into that second row now, that is a discrete function. Hopefully you spotted it as being discrete because it has a bunch of individual points that are not connected. But it is a function. Again, vertical line test, no problem. I'm never going to hit twice drawing vertical lines on that graph. Number 5 is a continuous, smooth curve, all connected, relation. And you can see right here, I could draw a vertical line, hit that graph more than one time, and that is enough to rule it out as a function. This is a relation. So continuous relation, as is number 6. Number 6 is kind of this wonky graph right here. And if I just draw this vertical line, not very vertical, not very straight, as I tried to freehand it, but you can see it hits in 3 spots in that case. And so way more than one. And so it fails the vertical line test, and we can label that a continuous relation. So guys, this is it for 2.1. I know we bounced around, hit a few different topics, a few different definitions, but this is really laying the groundwork for the rest of this chapter on linear equations. And so if you need to, email me or write down a question that you had while watching this video so that when we meet together, you can ask it. But rewind it if you need to, look through those examples again to make sure you have a good understanding. We will be discussing this in person as well. But for now, I'm going to leave it there, and I will see you next time.